asking for the speed. It's not a velocity, it's a flow rate. It's volume per second, not speed, it's not distance per second. So we want to know the volume per second. Well, along the vessel, even though there's a stenosis, it makes no difference. The volume per second is the same everywhere. Blood's neither created nor destroyed along the vessel. Therefore, the amount that's flowing across the stenosis per second is the same amount that's flowing at any other point along the vessel. So to calculate this, we can ignore the stenosis and just calculate it through the unobscured vessel, where we know the diameter. We don't yet know the diameter of the stenosis. We're asked to calculate that, but we do know the diameter of the unobscured vessel. So we make that calculation. So we know, so to calculate the blood flow speed, the velocity, we use that equation. Speed of sound times the Doppler shift, which we're told is 1 kilohertz in the unobscured part of the vessel, divided by 2 times the frequency, it's 5 kilohertz, times cos theta, cos of 60 is 0.5, and you get the answer that the velocity is 0.308 meters per second, or 30.8 centimeters per second. Now, to calculate the blood flow, the volume per second in milliliters per second, you need to multiply the velocity by the area. So velocity times area is the, well, velocity is distance per second, distance times area is volume. So area times velocity will give you volume per second that's running along the vessel. So the area is pi times the radius squared, half the diameter. So you put that in and you get the answer 6.05 milliliters per second. So that's the blood flow rate. Now, last part, sorry, go back to the question again. The question says, calculate the percentage of the cross-sectional area obscured by the stenosis. Well, we're told that the frequency increases by a factor of 3. It increases from 1 kilohertz to 3 kilohertz. Well, since we must maintain a constant flow rate, if the frequency increases by a factor of 3, that means the velocity increases by a factor of 3. So it's Doppler shift. Frequency is proportional to velocity, and therefore, if the velocity is increasing by a factor of 3, then the area must decrease by a factor of 3 in order to maintain the same blood flow rate. So if it's decreased by a factor of 3, then it's decreased to a factor of a third, so it's 33% of what it was during the unobscured part of the vessel, and therefore the actual reduction in the area is 66.6% or 67%. Okay, that's straightforward.
If we just use the continuity rule, just the equation.
Yeah, you get the same answer, yeah.
Isn't that the right view?
That's right, yeah.
Would you need to derive that equation? Is that when you can step?
The Doppler shift. From first principles, it has been an exam question in the past, I believe. But what you won't get is a question that says derive the Doppler shift equation. Right. What you probably get is some intermittent stages, and expected, yeah, to figure out various intermediate steps. Okay. So it'll be a more constructive question. Sorry? I wasn't going to give these out, but if you come and see me, I'll certainly have to print these out. Okay, question 3A. With the aid of a suitable diagram, describe the operation of a linear array ultrasound probe. Okay, so I thought to answer this, I'm just going to show you the slides I showed during the actual lecture on linear arrays. Remind ourselves what linear arrays says linear array as opposed to phased array, that refers to an array where we have usually several hundred transducers in a line with quite a large footprint, which generates a rectangular image. So we just pulse a group of elements on that array in turn in order to sample lines which are perpendicular to the surface, as opposed to a phased array, which is a smaller number of elements where the beam is steered by adding delays to the pulse within the group. So this is the linear array, which is the simpler array, which actually came first in terms of the development of this technology. So we have an array of transducer crystals, much larger number than I have in my animation here, and I illustrate this as if we're pulsing one at a time. We send a beam downwards, and thus we measure the echoes that come back along each line of sight, and we construct a rectangular image. Now, the number of lines we get in our image will depend on the number of distinct lines of sight that we can sample. Thus, if we want to get 300 lines, which is a decent resolution, then we need 300 elements. But if you pulse just one element, the length of the Fresnel zone is very short. So let's say we have 300 elements spread over 10 centimetres, or 8 centimetres, then each one is going to be the order of 0.2 millimetre across. And if we pulse an element which is so small, the effective radius of that transducer is so small that the length of the Fresnel zone, which is equal to the radius squared over lambda, is going to be tiny. And thus we don't get a very long Fresnel zone. We don't get the Fresnel zone is this narrow beam which we need to get good resolution, spatial resolution in our image. So that doesn't work. Instead, what we need to do is pulsing in groups. By pulsing in a group of elements, pulsing them at exactly the same time, we're able to have a much larger effective radius of our transducer, therefore a much longer Fresnel zone, but at the same time still have a large number of lines. Number of lines is only slightly reduced by pulsing in groups. And so the first line is sampled by pulsing groups 1 to, let's say, 4. The next line is sampled by pulsing 2, 3, 4, 5. The next one will be 3, 4, 5, 6, and so on. And so you advance the group one transducer at a time. So the number of lines is still pretty much equal to the number of transducers, yet that we have enough within the group to get a nice long Fresnel zone. So this animation shows groups being pulsed. Transducers pulse in groups of 3. If we have n transducers in our array, and we pulse in groups of size k, then the number of sampled lines, I hope it's intuitively obvious, is going to be equal to n minus k plus 1. If you need persuading of that, just put some numbers in. So make n 100, k 5, and you'll see that the number of lines must be 96. The first one is going to be 1 to 5, the second one is going to be 2 to 6, the third one is going to be 3 to 7, and the last one is going to be 96 to 100. Therefore, there must be 96 lines. Okay. Question 3b. A linear array probe of length 80 millimeters consists of 120 elements and is operated in groups of 15 elements. Calculate the maximum scan depth in tissue if images are displayed at a rate of 75 frames per second. There's always a question like this every year. It's something that where where you're relating a scan depth to frame rate to pulse repetition time and so on. So, first thing you need to do, we know we've got 1/75th of a second to display the entire image. And we know how many different lines we need to sample. We can calculate very easily. And we're limited by the time it takes for the pulse to travel down, for the echoes to come back up. And we know that we've got 1/75th of a second to sample every line. Thus we can calculate how far the pulse can travel and the echoes can come back up before we need to move to the next line. Well, first of all, calculate the number of lines in the frame, in each image. Well, we have 120 elements. They're pulsed in groups of 15. Therefore, the number of lines in our image will be 120 minus 15 plus 1, or 106. Should be able to calculate that very easily. So the first one is going to be 1 to 15, the second one is going to be 2 to 16, and so on. And the last one is going to be 106 to 120. Therefore, there must be 106 lines in the image. So you can then calculate how much time is available to sample just one line in the image. Well, we've got 1/75th of a second to display the entire image. We've got to acquire all the data from one image in 1/75th of a second. Therefore, the time available to sample one line is going to be 75th of a second divided by the number of lines, or 106. Now we know how much time we've got for the pulse to go back down and for the echoes to come back up. What we also know is the velocity of sound in tissue, which is constant, 1540 meters per second. Since velocity equals distance divided by time, we know the velocity. We've now calculated the time available for the pulse to go down, the echo to come back up. Therefore, we can calculate the distance that the pulse can travel before we need to move on to the next line. So the total distance travelled by the pulse is going to be velocity times time, and therefore velocity times the time available, which is calculated there, comes out as 19.4 centimetres, and that is the total time, that is the total distance travelled by a pulse. In terms of scan depth, we've got to halve that because the pulse needs to go back down and the echoes need to come back up in that time available. So the scan depth is going to be half that distance, or 9.7 centimetres. Very standard question, usually asked every year in some form or other. You might be given the maximum scan depth and asked to calculate the maximum frame rate, for example. Then says, use your result to estimate the minimum frequency of the probe if the length of the near field, the Fresnel zone, is not less than the maximum scan depth. Okay, well we know the formula for the length of the Fresnel zone. That's the radius squared over lambda. And therefore, we can calculate what lambda must be in order for the Fresnel zone not to be any shorter than that maximum scan depth. So the length of Fresnel zone, a squared over lambda, approximately. A is the effective radius of the transducer. Obviously this formula was calculated, a squared over lambda, for a circular transducer. Our transducer, in fact, is a line of transducer elements in an array. So the effective rate is essentially half that group length. And that's, we put the numbers in. So we know we have 120 elements in over a length of 80 millimeters. Therefore, the transducer length is 80 over 120. Multiply that by 15, which is